Good morning, good afternoon, everyone, and thank you for joining us today. I'm Ashley Skitt. I'm the Director of Marketing here at Tempo, and we just want to say thank you for joining our webinar. Welcome to our webinar today titled Locating and Identification, Finding Cables and Identifying Wires. So we're just moments away from this awesome content. I see a lot of people still joining us today. First, a couple housekeeping things. The webinar is being recorded and will be available in 3 to 5 business days on our website. Go to tempocom.com and you can go to our education tab and you'll find our pre-recorded webinars and upcoming webinars there as well. So check that out. All the attendees today are on mute automatically. Please do use the chat to ask questions. We welcome that throughout the webinar. We'll answer all the questions at the end. And also this video is being recorded. Your presenter today is Mark Govier. He is the product manager over Tempo's wide range of telecommunications, Wi-Fi, and buried utility market products. Mark is a talented electrical engineer with 30 years of experience with design and development of Tempo products as a senior engineer and product manager. Mark, take it away.
Yeah, hi everybody. Well, as we say, this is going to be a fundamentals webinar. I've actually pre-recorded it so that I can hopefully answer your questions as we go along through the chat, but we'll see. We'll probably keep most of them to the end and go through it that way. But anyway, let me share my video of the presentation, and we'll get going.
Hi, I'm Mark Govier, Product Manager for Tempo's wire tracing and locating products. Welcome to one of our Fundamentals series of webinars. This webinar is targeted at beginners and those who want a refresher on how things actually work and why we do things in certain ways. Today, I'm going to be talking about the differences between identifying wires and locating cables, which techniques to apply when, and mentioning the shortcomings of each technique and how to overcome these. I will be starting from the real low-level fundamentals, which is necessary to understand why certain things work and others do not. There will be a live questions and answers section at the end, so please feel free to pose questions in the chat whilst this presentation is underway. We are going to clarify the differences and similarities in techniques used to locate and to identify cables and wires. In this first section, I'll introduce location. Finding the location of cables which are not currently visible is important if you want to avoid damage to buried cables, or you know there is a fault present and you want to uncover the cable to repair it. Safety is the #1 priority, but there are also huge costs associated with damage to buried plant. Let's consider why you're heading out to find a fault in the first place. Most likely it's being caused by someone else's actions who may not have been aware of the presence of your cable. Cable location is key to cable avoidance too. If you know it's there, you can avoid it. Once you have located a cable or a set of wires, which one of them are you interested in? Let's look at wire identification. Wire and pair identification is important when there is doubt about which wire does what. Perhaps you're wiring a house or a factory, installing an alarm system, or running telephone or Ethernet cables. Which one goes where? In the ideal world, everything will be neatly labelled and colour-coded, but this isn't the ideal world. Wherever there is any doubt about which wire goes where, wire identification techniques can help you, applying a signal to the wire you're interested in and seeking that signal elsewhere. I will now introduce the fundamental phenomena that we can exploit to locate and identify wires and cables. Let's start by going back to our basic physics classes on electricity and magnetism. Remember that these two are very closely related. Electrical potential between any 2 points can result in current flow. Those currents can result from a potential being applied to a conductor and refers to the amount of electrical charge that flows per second through the conductor. Magnetic fields in their raw form are weird, and both B and H are confusingly often both called the magnetic field strength, but are interrelated by the magnetic material's vacuum permeability. Quite enough of that. You're very welcome to start teaching yourself more about the fundamentals of how and why magnetic fields exist in your own time. Learn enough and you may get yourself a Nobel Prize. The previous 2 slides have presented the fundamentals that we can base electromagnetic location techniques upon, but there are constraints. Let's discuss them in a few more slides. Ground, or earth, whatever you call it, ground is the local reference for all potentials. Let's also think of it as 0 volts. Most soils, particularly if slightly damp or moist, also have varying degrees of electrical conductivity. Conductive soil will shield electric fields, preventing them from reaching the surface. However, magnetic fields will pass through most soil unaffected and is only slightly attenuated by iron-rich clays. Keep both these facts in the back of your mind. In 1600, William Gilbert, Queen Elizabeth I's physician, observed that a light metal needle that was non-magnetic could be made to rotate by bringing close to it something that was later found to carry an electrical charge. He used an amber rod to deflect his versorium. Amber is known as electrum in Greek. That's where we get the root of the name for electricity. He also distinguished the force of electrical attraction from magnetism. More on that later. This technique was later, in 1731, developed to become a pithball electroscope. But in 1787, clergyman Abraham Bennett created the far more sensitive gold leaf electroscope. You might have seen some of these in school. That was sensitive enough to deflect the leaves, the gold leaves inside, by induction and not necessarily requiring connection of the charged article to the top. This led to the understanding that static electricity is basically everywhere that ground isn't. Whether it's the 2 terminals of a battery or the output of a huge power station, wherever there is potential difference, also known as voltage, there will be an electrostatic field. One terminal will have a different voltage or a potential to the other. One positive, the other negative, relative to each other. Between the 2, there will be a point where the net potential is 0. The E, or electric field, may be steady as from a battery, or the static electricity from a polyester shirt, or alternating, such as from mains electricity or an oscillator. More on that soon. In 1600, William Gilbert, yes, the same one who messed with amber and pivoting needles, published De Magnet. I'm not even going to attempt to read the original Latin title, but in English, On the Magnet and Magnetic Bodies and on the Great Magnet, the Earth. In this book, he cleared up the various discussions that had been ongoing that it was the Earth itself that was magnetic, not a large floating island in the north, nor the star Polaris that caused compass needles to point northwards. But this all-prevailing, largely unchanging or static magnetic field is also present more or less everywhere on Earth, useful for navigation and even very roughly telling you your latitude. When the potential or voltage mentioned in the earlier slide is applied to a conductor, then a current will flow. That current is proportional to the voltage and inversely proportional to the resistance of the circuit. We're still assuming DC here. I equals V over R. I told you we're going back to basics, so here we have Ohm's law. In April 1820, Hans Christian Ørsted was the first to document the observation that an electrical current flowing in a wire would cause a nearby compass needle to move. In 1831, Michael Faraday discovered electromagnetic induction. That the reverse also occurred. Changing the magnetic field near a wire could induce a current. It was only a small step to then realize that coupling two wires magnetically was possible, basically inventing the mutual inductor, or as we sometimes call it today, a transformer. Current flowing on one conductor causes a magnetic field, which can cause a current to flow in another nearby conductor. By its very nature, induction is an alternating current, or AC, effect, caused by alternating or a varying magnetic field. Here, or in a transformer coupled between two coils, by the iron ring core that concentrates the magnetic field. If things change or alternate in a regular way, then this can sometimes be easier to detect. Whilst there may well be some static parameter in the background, if our measurement system is only looking for periodic changes in that parameter, then we can effectively make our detector ignore those static fields and other noise, whether they be static electrical potential, aka voltage, or static magnetic field, e.g. from the Earth itself or a permanent magnet, or a DC current flowing in a conductor. This is why, for practical cable or wire identification, a tone generator or other alternating signal generator is needed to create the alternating field of potential and/or current. How small are these alternating things? MRI machines have absolutely massive but largely static magnetic fields in that small space in the middle, strong enough to magnetically constrain the nuclei of atoms so that they can be excited by an external radio frequency field and tested for resonance. Everyday objects with permanent magnet motors like refrigerators or windscreen wipers have local fields that are hundreds if not thousands of times less powerful than the most powerful MRI scanners, but are still thousands of times stronger than the Earth's own field. But the field 1 meter from a wire carrying what is a large tracing current of 40 milliamps is around 10,000 times smaller than that of the Earth. Yet this is normally readily detectable because it is made to alternate at a predictable frequency. When static electricity builds up on a surface, it can act a bit like that pithball electroscope. See this cap here covered by expanded polystyrene packing chips, or the hair of the young child who's just descended that plastic slide. Each strand of their hair is acting like the gold leaves of an electroscope and repelling each other. You will have often experienced the sudden discharge of static charge when getting in or out of your car or pulling something out of a plastic bag. The potentials involved are always in the kilovolt range. Now consider how we're going to identify a wire from others with such static voltages about. To do so, we must ignore the static or background electric fields and only look for some alternating voltage, but also using a significantly higher frequency than the local mains power. Let's start by looking at how we can apply electrostatic detection to identifying individual wires from a bundle. We use an oscillator or a toner to apply an alternating voltage to the wire or the pair that we want to trace. In this example, we show just one conductor being sought relative to ground. The signal generator is connected between this conductor and the local ground. The conductor carries the electric field or the influence of that voltage towards its opposite end. That potential creates an alternating electric field around the conductor. The tip of the amplifier or probe is conductive and senses the electric field around the conductor. Direct contact is not needed. You can detect the potential of the electric field outside the wire's insulation, for example. This tip connects the input of a sensitive high impedance amplifier, whilst the amplifier is grounded by mutual capacitance to your hand. You can adjust the gain of most amplifiers, and they may be equipped with a speaker or a headset, and some have signal level indicators. Clearly, this is also how non-contact voltage detectors work to detect 50 or 60 Hz mains electricity. Keep your mind thinking about the electric field when tracing wires. The conductor ducts the electric field to where it's wanted. Intervening soil, actual ground, or grounded metal can ground or shield that field. As the field surrounds the conductors, it can couple to other nearby ungrounded conductors. We call this crosstalk. It's one of the reasons we use twisted pairs, as the field applied across one pair averages out to a net zero when looking at adjacent pairs. It is important to remember that signal tracing amplifiers have very high impedance inputs. If you place your finger on the probe tip, remember that your hand is also the local ground reference for the probe. Then you will partially short the signal being detected. When tracing a wire pair, particularly if that is a twisted pair, provided you connect the tone generator across that pair, then there should be a null detectable between the two wires. Ground is ground and therefore zero. You are approximately at ground potential too. Electrostatic detection works best for disconnected wires and cables. If the wire is terminated to some circuit or shorted to ground at some point, the potential detectable may be reduced. If the termination or short is low impedance, that remaining potential could be close to zero. You always have to consider what is or may be connected at the far end, or what faults exist on the cable you're checking. If a conductor is shielded by a metal screen, foil, or metal ducting, or conduit, or even damp soil, then no potential will be detectable outside that shield. Let's give you a simple practical demonstration in this attached video. This shows how electrostatic pair tracing can be done. Okay, here we have a simple household 3-pair telephone cable. I've applied a tone to one of the 3 pairs, and let's sort of see how pair tracing actually works in real life. So if I first of all turn on the probe, you can hopefully hear that there's something beeping away in the background, so there's something going on. But let's demonstrate what happens with shielding. So if there's something that's grounded in between the cable and you, first of all, very little signal gets through. Then, let's look at the cable, and here we can see the light flashing, we hear quite a loud tone. And as I move it along, because the twist in the cable moves the cable further towards the front and the back, the signal gets quieter and louder as we move along. So here we know that the pair is near the surface of the cable. So now let's look at the end of the cable and the electric field as we get to the end. So we have 3 pairs. We have a blue, an orange and a green pair. There's something here. Ignore the power warning. So there's something there. There's something there, but that's probably quieter. But this is significantly louder. So we can see that the green pair is making quite a big signal. Now if I'm very careful, somewhere in the centre of that there's almost a null. Loud, null, loud. Whereas for the other pairs, there's no change. Loud, loud, quieter. And if you're very careful, you can actually find a real null. But this is the pair with the signal on. And again, if you get your hand in the way, it shields it. If you touch the tip, it attenuates it. So these are things to avoid. Beware of the shield, and be aware of where you're grounding. When you can't see the cable, perhaps it's behind a wall or buried in the ground, or electrostatically shielded, how do you find it? First, we need to set up an alternating electric field on the conductor and make a circuit so that we can get the electrical charge to flow, forming a current in the conductor that we want to follow. That current, once established, will develop an alternating magnetic field around the conductor. The easiest way to do this is to connect a signal generator or oscillator, sometimes called a transmitter, directly between the conductor and ground. Ideally, short the far end of the cable to ground there too. Otherwise, you will be reliant on only the cable's capacitance to ground to develop a current. If you cannot short the far end, then the final length of cable, that length depends on many variables, will not be detectable, as the current will tend to zero in that final section. For magnetic location, the amplifier, instead of having a voltage probe, is normally equipped with a search coil that develops a signal based upon the magnetic field passing through that coil. Here, we're using magnetic induction. The voltage establishes an electric field along the conductor. Because that conductor forms a loop due to being shorted to ground at the far end, a current flows. That current creates the alternating magnetic field. That magnetic field can be sensed by using the search coil to couple it. The level of coupling is related by both position and orientation of the search coil to the conductor. Direct connection of the transmitter to the cable as shown on the previous slide is always the best option. However, this may not always be possible or desirable due to having to maintain service or wanting to track services that you don't own. In these cases, you can use a current clamp to place a temporary magnetic circuit around a cable to directly induce current, or most locator transmitters also include an induction antenna within their case. Placing this alongside or above the cable to be located will also induce a traceable current. Just imagine the search coil operating in reverse. A multi-turn coil is creating a magnetic field above ground, which can induce a current into any conductor below ground. That current will be ducted as a current by the conductor and can be sensed further along the cable by a search coil. Remember that drawing from an earlier slide showing the magnetic field developed around a conductor that is carrying an electric current? Let's think about how the search coil might sense that field, particularly with regard to identifying the precise location of the conductor or its depth. When the search coil is oriented at 90 degrees to the path of the cable, then the maximum number of magnetic field lines will couple to the coil, giving a peak in the signal. This is great for following the route of the cable and is great for most purposes. By adding a second horizontal search coil, a known distance above the primary ground level one, the machine can estimate the depth of the cable by simply comparing the two signal levels. If a search coil is oriented vertically, it will detect a signal either side of the cable, but will present a very sharp null when directly over the cable. Once the cable has been located and marked, you can move a little to both sides with the coil oriented at 45 degrees towards the cable. When you find the null to the side, the distance to the side is equal to the depth. Checking both sides allows you to get a clue as to any magnetic interference or field distortion that might occur from reinforcing bar or iron pipes, etc. Electromagnetic location works to trace current flowing in a wire. Remember that the transmitter's output needs somewhere to go and to return. Normally we do this by grounding the far end of the cable. However, if you're trying to track down a short, then that can achieve what is needed too. Because we're utilizing the magnetic field to trace, then normal, relatively thin electrostatic shields around wires or thinner cable ducts will not attenuate the magnetic field. So take your favourite locator and let's place it on the ground near the cable you want to trace. Bring out the ground stake, place it at about 90 degrees to the root of the cable. Take the connecting leads, hook one of them to the ground lead and hook the other one to the cable you want to trace. Then take the two wires and connect them to the transmitter itself. And as recommended in the instructions on this one, turn the control to about 3 or 4. Take the locator wand and then we'll turn it on and just check that something's being transmitted. That appears to be working. So then we'll walk to follow the cable, and here we can see that the needle will deflect to the right when there's a good signal and drop when you're moving away from the cable. So let's walk away from the start and start following the cable properly. So little signal, strong, weak, strong. Here we are. Adjust the gain if necessary and just follow the cable. What I'll show now is switching over to using the BLL. Okay, it's a different transmitter as well, but the BLL shows a very similar function. So you get a peak as you go over the cable, and you get a lower signal off to the side. Now the one advantage of the BLL is it's got simple push button control to measure depth. Let's try to put all this in a few key points. Depending on your role, you may need either or both technologies in your arsenal. Electrostatic wire identification to tell apart individual wires and pairs, and magnetic location for cables and wires you can't currently see. Remember that both techniques rely on alternating signals standing out from background static electric fields or the Earth's magnetic field. Now, I'll summarize several of Tempo's products that can help you. We will send you all a copy of this presentation, and you can follow the links to each product's webpage, allowing you to get more details. 601K is a great simple pair tracer that has been used by telecom technicians for decades. This kit implements everything you need in a basic pair tracer. 701K is the 601K's bigger brother, which adds a few features that are desired by some professionals. The 77 HP toner adds the option of angled nose plus better nails test clips, audible continuity testing, and dual line polarity checking. Then the 200 EP probe has signal strength indication, headset connection, and a flashlight. The 801K has the 200 FP probe that includes a magic power hum rejection filter, making your job easier when tracing around other electrical equipment. Remember that electric field we're tracing will be present at 50 or 60 Hz around all power cables too. 200 FP effectively eliminates that hum and just leaves you with the pair tracing tone that you're looking for. 24BK uses the same 200 EP probe as the 701K, but replaces the toner with the 24B Station Master Pro irrigation tester that includes special functions which are great for irrigation technicians, such as checking for 24 volts AC from the clock, solenoid activation with checking for normal solenoid impedance, and solenoid chatter mode. 811K is a more advanced version of the 801K. The toner in this kit is a 77GX, a microprocessor-based precision toner, and the probe is 200XP, which adds a precision tone filter mode to the 200FP's power hum filter. This can be useful in situations where there is more broadband noise. 500XP is a fully digital signal processor-based version of the 200XP precision tone probe, but in a rugged and water-resistant enclosure that is ideal for use in the field. It floats if dropped in a puddle. 88LK combines the 88L LAN toner with a 200 EP. The 88L combines a modular adapter allowing connection of the terminals to any pair of wires or to split across pairs for Ethernet cables. Plus, it can indicate the presence of link pulses from a connected switch or PC, or can blink the activity LED of a remote device. The ability to split the signal across pairs is great on that super twisted Cat5 and Cat5 above cables. 620K combines the 200 EP probe with the PE620 security and alarm toner that are special modes to detect normally closed and normally open circuits, with latching functions to help diagnose intermittent faults. Tempo offer a range of cable locators, from the simple handheld 402K, which looks a lot like one of our wire tracers, but also includes a search coil near the electrostatic tip, right through to the 521A, which is optimized for use by irrigation technicians. 501 and the 508S are similar products utilizing high frequency for cable location. The 501 kit, including a more powerful transmitter, an induction clamp, an induction antenna, and a probe designed for use whilst walking, whereas the 508S has a short-range, direct connection only transmitter and a handheld search coil. This is great for use in a building or in an access chamber. BLL200, buried line locator, is a comprehensive cable locator and cable avoidance tool that can allow easy cable tracing with or without the transmitter, as it has a broad frequency reception, passive mode, that can follow the noise on active cables in addition to its location mode. It has a coupling clamp and an indirect coupling antenna in its transmitter. And then the 521A, as mentioned earlier, is an irrigation locator optimized for following cables to solenoid activated valves. On the next slide, there are a few links to some more information. You might find the information in these links quite interesting, particularly the last one. It gives a lot of interactive animations of several of the aspects we've been talking about today. We've been talking about electromagnetic signals throughout this presentation. I want to just clear up a little bit of possible confusion. This is just a quick note on the fact that we and other people talk about cable location using electromagnetic means. Whilst there is a possibility of generating a propagating electromagnetic wave when using cable location techniques, most cables being sought are relatively short compared to any likely propagating wavelength. For example, 33 kHz used by the BLL200 would have a wavelength of about 10 kilometers or 6 miles. So on longer overhead cable run, there is a chance of a small amount of energy being transmitted. The levels are likely to be small due to the limited height of the telephone poles compared to massive low frequency antenna systems. But when detecting electric potential, then a little current is flowing and a wave will not propagate. To get electromagnetic waves to propagate efficiently, you need an antenna, something that combines the electric field and the magnetic field to form a propagating wave. Everything you've seen today is part of electromagnetics. The key thing is to think about the fields and how they affect nearby objects. When you want more comprehensive training on any of the specific products, then please do contact our customer service team. Watch out for our regular videos on YouTube and follow our announcements and competitions on social media, including Facebook, Instagram, and LinkedIn. So, I'll pause the recorded system now, and do you have any questions you'd like to ask?
So I hope you've learnt something new today. I don't see anyone tapping anything in the chat window. So we have got a couple of questions which some of the people in our company have put towards me. So the first thing was, can I use a tone probe to find a buried cable? Well, that goes back to one of the slides where we were trying to talk about the ground, or if you remember, I put my hand between the wire and the actual tone probe, and that actually attenuated the signal. So my hand, think of my hand as being a piece of wet soil. It's the same stuff as far as electric fields are concerned. It shields the electric field from that cable reaching the electrostatic tip of the tone probe. So if it's behind soil, certainly wet soil, I mean, if it's in absolutely dry sand, there is a possibility, but again, anything more than a couple of inches and you know, electrostatic tracing becomes tricky. So when it's buried or hidden, the magnetic location, so whether you're using something like the buried line locator or the 508S, are best. So that also goes for wires which are behind plasterboard or drywall, as it's sometimes called, especially if it has foil backing. So quite often the water resistant or more vapor resistant versions of those materials will have a foil on the one side, and that will actually completely act as a shield to any electric field. Okay, Justin has just put a question up here. So which is the best system for locating underground insulated copper wire? In his example, it's the sort of invisible pet fence gadgets. These are also used, for instance, if you've got one of those automatic lawnmowers, you actually lay a wire around the outside of the grass area to stop the thing wandering off and cutting your flower beds. So these wires are normally continuous from one end to another, and whilst they're continuous, they work because they're using exactly the same technology. They are actually a cable locator. The transmitter, which sits back at the base, where there's either transmitter which tells the dog collar to inform the dog not to stray further, or the one which tells the robot lawnmower to stop going forwards and turn around and go off in a different direction. That has a transmitter at one end, and then the actual receiver on the dog collar or within the lawnmower unit is usually a search coil, as we showed in one of the slides, which will, as the thing approaches, will detect the electric field around this wire and go, oh, the field's getting stronger, I'll turn away and go the other way. So to do that, normally you would use the device itself, but you're talking, Justin, I guess, about a broken wire. Now this is where it becomes tricky, because obviously if the wire is completely severed at some point, you have a problem. And what you can do, you can use an underground locator, but you'll probably want to use a higher frequency one, because the higher frequency can be coupled onto the end and it will carry further along the cable towards that open broken joint. And as it approaches that broken joint, there will still be current capacitively coupling to ground. So you'll be able to trace it closer to the break. You probably would be able to get within a foot or two, because these things are usually buried 6 or 8 inches down. So you can probably get to within a foot or two of the break, and especially because it's meant to be a loop, you can trace the other side as well, and you'll certainly have a hole which you can access then, which is probably a couple of shovel widths wide to access the cable. So that would probably be something you would probably want to use either a 501 or the BLL 200 for doing that type of job. So again, another question that came in earlier was trying to differentiate between the peak detection and the null detection for cable location. So again, we've got the current flowing down the cable, could be a pet fence wire, doesn't really matter. But your locator will have the search coil on the end, either on a horizontal form. So if I use my pencil here, so it'll either be horizontal. If you imagine the cable is running from my chest towards you guys, and there's a current setting up a magnetic field which is around that cable, then when the coil is in this format, as you move the search coil over that wire and it comes directly above it, the maximum number of field lines will be coupling with that, so you'll get a maximum of signal, which will drop off gradually as you move off to either side. So there's a peak, but it's not super well defined. But the trick is, if you can use a locator with a vertical search coil, those same field coils, field lines on the magnetic field from the cable are still oriented the same way. But if you move this off to the side, this is now coupling with some of those field lines. When it's directly above the cable, all the field lines are actually perpendicular to this search coil, and virtually nothing couples. So there's quite a strong signal as you come towards it, and then as you go directly above the cable, there is an absolute definite null. It is important to actually check from both sides, because if you imagine this, say this was a 2-foot down 3-phase power distribution cable, and above it there was an iron water pipe or something, that magnetic field could be distorted by that iron pipe. So you'd actually check from both sides to look for a different shape in the field as well. But the beauty of the vertical coil is you can get a very, very good precision location vertically above the cable. So Justin is now asking again about the BLL200. Can you explain a little more about the latching feature and how it can help with locating intermittent faults? We call them partials when the wire is partially damaged, but there is intermittent continuity, so the system sometimes works but sometimes does not. I think I'm trying to understand what you mean by latching feature. There is an automatic gain control feature on the BLL200, if that's what you mean. Do you want to put to a thumbs up if you mean that? Or I could actually just turn your audio on, I think. Can I do that somehow? I'm trying to... Yeah. I can't see how to... right click.
Mark, I think Tyler has to do it
Oh, okay.
to turn his audio on. And I just asked him if he could do that for us.
Okie dokie. Yeah, well, hi, Justin. Yeah, I heard intermittent faults. I was unsure if I was thinking the same thing. Well, an intermittent fault could be, yes, as you say, something which is, you know, a corroded joint or it's a mechanically intermittent connection. And again, what you might want there, I mean, it's intermittent. It's a bit like the completely open circuit. The open circuit, when you're trying to trace underground, is the one problem you don't want. Everything else is easy to find underground, but the open circuit is the tricky one. It's the one where you might end up digging a 1 meter hole rather than a tiny little hole. Now, intermittent faults, they're always the ones which are difficult to find, whether you're debugging your washing machine or a piece of cable. That's all I'm going to say. So the connection will be coming and going, and the level will be changing all the time. So yes, unfortunately, with BLL, you would probably be resetting the gain quite often. So Troy is asking, how does the BLL calculate the depth, and is it accurate? I have actually recorded some other video, and I was going to try and put some more into the presentation, but it was getting a bit long. Yes, it calculates it by simply having 2 of these surge coils. So we've got the same cable coming out of my chest, going towards you guys, going by here. So there's 1 surge coil here at the bottom of the foot. And then when with the BLL200 you're making a depth measurement, you have to extend the leg because it's an extension. It's like a part of a photographic tripod. So you stretch it out and clamp it. And then the 2 surge coils are a fixed distance apart. And what it can actually do then is calculate the difference between the measurement at the foot and the one up near the handle. And it calculates the depth, and provided the signal is reasonably strong, and I mean not super strong, provided you're getting some LEDs lighting up on the display, it's accurate to it shows to a decimal foot, so 0.1 of a foot, so just about an inch, and yes, it is. I would actually argue that when I've compared it against others and actually looked in holes, it is accurate, provided it comes back to that caveat again, that there is nothing in between that is causing a distortion of the magnetic field between the lower antenna and the upper antenna. So if you're tracing very close to a steel wall or something like that, that is probably not ideal. But in the normal street environment where you've just got concrete, especially if it's not reinforced, then there is no issue with the depth measurement. It is pretty accurate. I would trust myself to dig on that. How do you calculate depth with the vertical probe? Okay, so this one is quite easy again to demonstrate. So we know that with the vertical probe, because the field lines around the single conductor are circular, as long as they're not distorted. And this is where again you make the measurements to the left and right. So the first thing would be to do is to trace your route. So you'd go along the route, marking the center line of the conductor. And if you wanted to check the depth, you would find that null. You would then orient your search coil at 45 degrees, give or take, and then move it off to the side. And of course, when it gets over to here, that is then again at 90 degrees to all the field lines around this cable. And you would repeat the same on the opposite side. And you would make sure these measurements you made on either side are the same. Because that measurement, this being at 45 degrees, that must be a right angle triangle formed between the depth and this distance across. So we just have that lovely geometric depth with the 45-degree probing. So it's very easy to do, and with the 501, sorry, the 521, which we use for the irrigation system. The other advantage of having that vertical probe is you can follow your irrigation wire out towards the station valve, the solenoid valve, and when it comes over that solenoid valves are meant to be oriented vertically. So if they're put in correctly, the coil is vertical. The beauty is that current runs along into that coil and then runs around that coil, and that generates a huge field going up this way. So you've been following your cable and it's giving you a null. And as you come close to the valve, you'll suddenly find that the null starts to disappear because it's getting swamped by the field radiated from the coil itself, which is obviously oriented vertically. Did that help? I hope so. Thank you. Yeah. Okay. Thanks for that question. Any other questions? We've got a few more minutes.
We had one talking about asking if you can touch on tightly twisted pairs and signal canceling.
Ah, yes. I only glossed over it in the presentation, but one of the reasons why twisted pairs are used, if you think back to the ancient days, the end of the 19th century, when there were overhead cables. I hope none of us are old enough to remember actually working on those, but you'd have the overhead cables, and even though you'd have these two wires running on the pole, every fifth or sixth pole they would actually swap over and then run again for another 5 or 6 poles and then switch back again and carry on. So even back in the 19th century, the 1880s, 1890s, early 1900s, those were twisted pairs, but they weren't squashed into one single tiny bundle. The reason we do that is that if you imagine around each of those wires, there is a current flowing and there's a voltage potential around it. So as in the one drawing there, it shows the two wires, one's positive, one's negative, and it shows the electric field between the two. But if you also imagine there's a magnetic field, the current's going forward in one way and coming back in the other way. So those two magnetic fields cancel themselves out. And by having those wires cross over each other as they go along that cable, and then the other wires within the same cable crossing over as well, but not at exactly the same speed. So especially in a category 5 or 6 cable, the actual twist rate on those twisted pairs is very, very slightly different. And that means that given an average, I mean, Cat 5 and whatever twists several times per inch, and telephone cables perhaps once every 2 inches. Given 10, 20 twists, any influence of external electric and magnetic fields or the individual fields between the different pairs cancels out. So that was the beauty of a twisted pair, is the fact that those fields cancel out. Now that brings a problem. I did a demonstration with a telephone twisted pair in the video, and the reason I chose that was because the twist is that 2 or 3 inches long. You can actually go along it, you can find the difference. When you come to a tightly twisted cable like a Cat 5 or 6 cable, unshielded of course, because remember that shield that would be on the outside would shield everything and you wouldn't get anything. If it's an unshielded twisted pair, so UTP, then the twists are several per inch, and it's very difficult to find that little sort of change of level. But you will find that because the 4 pairs within a Cat 5 cable do twist over several inches as they go along the cable, you will find that if you apply signal to a pair, as you go alongside the sheath of the cable, or the insulation of the cable, you'll find the signal coming loud and quiet, loud and quiet. But if you want to trace Cat 5, the best thing is to split the signal. If you remember, we showed one of the products, which is an 88L, which looks like a big modular adapter with the tone generator built into it. That basically allows you to take 2 leads and split them across 2 different pairs, so you could put it onto the brown pair and the green pair or something. And that means that the pair tracing signal is not applied across a pair of wires. The beauty of that means you get a little bit more radiation further from the cable, so you can find it. And also, if that cable is in use and plugged into a patch panel or a computer, then it's not across a transformer. A transformer at the frequencies we do pair tracing at would be as short, and there'd be no signal to detect, or certainly as you get close to the end. So yeah, split it across 2 different pairs. Either use a modular adapter along with your standard 77 HP, or use the 88L. Troy's asking another question. So is locating electronic markers and marker balls or disks the same method of locating? It's related. Again, it's magnetic induction. And the way it works, for anyone who's not aware, we make resonant electronic markers. And they come in the form of a ball. We used to do ones which were in the form of a disk, and that again may come back. But we make these ones which go in a ball. You tie wrap them or bury them alongside your service. They're ideal for use with services which have no normal conduction. So things which are like gas pipes, plastic water pipes, fiber optic ducts with just fiber in them. Use these markers, especially in the key points. What they're actually resonant circuits. So it's an LC circuit for anyone who's done any radio or amateur stuff, hobby electronics. You've got a coil, and you've got a capacitor across it. It tunes it to a key frequency, and then we have a special locator. It's not a cable locator, it is a marker locator. Some people make versions which are combinations. They're quite expensive. But we do this one which just does the markers. It pings down a frequency at a time. Ours actually does a scan, so it has a scan function compared to others. But it pings down all these different frequencies, and if it sends down the frequency, if there's one of these resonant devices down there, it's like pinging the bowl, one of these sort of like Hindu prayer bowls or whatever, or Buddhist prayer bowls, or a tuning fork. You hit it, it rings for a little bit of a period, or a bell. This thing will ring for a few milliseconds. It's not very long, but the transmitter can transmit a burst of energy at, say, 66 kilohertz. This thing might ring at 66 kilohertz, or it might be a telephone one at 101.4. So whichever frequency it responds to, it'll ring, and it'll die down over a fraction of a second, and the locator can find it. So it's inducing a signal downwards and then receiving a signal coming back. So that's the markable. So it's related, all absolutely related. It's all Michael Faraday's fault. In fact, I found a very interesting video about the history of electric fields and even the speed, even the propagation of electromagnetic fields as waves, which was postulated by Michael Faraday before anyone else. So I will probably add that as a link to the presentation before we send it out to you all.
Thank you, Mark. I think that's probably all the time we have for questions.
Okay, absolutely. So now, I think there was a prize available for some people if they wanted to take part. So what we have is a poll, and there are 3 simple questions. It's just to check they were paying attention. So what I can do, I will launch these. I'll give you all about 20 or 30 seconds for each question. So I'm going to start my watch now. So launch the first question. Hopefully that can be seen. Can you confirm that?
Yes, we can see it.
Good. It took a while for my system to respond back and say it was live, so I'll time it from that point. Okay. I will now launch the second poll. I assume it cancels the first one.
Oh, someone's saying the quiz is not submitting answers. Are you seeing answers submitted, Mark or Tyler?
Let me view results. Yeah, we've got. I had 12 responses.
Oh, yeah.
I can.
Two people are saying they can't submit.
I'll try restarting it at the end, and so just hopefully you can do it on this one. I must admit we've only really tested this on a PC, so maybe it's different on a phone or an iPad or something.
It worked for me, so hopefully some people, yeah.
Yeah.
So.
Okay, I'll start the third one.
So it looks like a number of people can't submit their answers. We
No,
apologize. Looks like maybe on mobile and.
Not sure about that. We'll have to do some more testing before we do this again.
Yeah. So
sorry about that.
The giveaway we'll draw from all the people that attended the entire presentation.
I think that's the fairest thing to do.
Yeah.
But it's a nice little quiz anyway at the end.
How'd our audience do, Mark?
Interesting. Pretty good. Yeah, especially on the middle question. Okay. I'll summarize the results in the presentation when we send that out, as I say, with that extra link around some of the history of this as well. Okay.
Well, thank you everyone for attending. As I said, this webinar will be posted on our website in 3 to 5 business days, and continue to look there for future upcoming webinars. Mark, if you don't have anything else to add, I think we can wrap up.
No, I don't. Thank you very much, everybody.
Thanks, everyone. Bye.
Bye.